Hello everyone, I welcome you all to the practical session of day 2. So today we will learn about the image analysis of microscopy using ImageJ. Before we start learning, let me take you to the couple of introductory slides on digital images and why we need image analysis. So what is digital image? An image that is taken through digital device like cell phone, camera or any digital means. Okay, so now what you see in this image, an eye. So if you little zoom in, you can see details. Further zooming, you can see more details. But for how long? Finally, you will reach the smallest detail of the image. We should understand the computer do not see an image in a way we can see. For a computer, this image is just a set of information about each smallest point in terms of color depth. Generally, we call that smallest feature of the image as pixel. Technically, a pixel is a physical point in the raster image or the smallest addressable element in an all-point addressable display device. It is also known by the name PEL or pixel element. Now, computer or digital storage device store information about each pixel in the form of bits. Larger the name of color in the image, more bits and more information per pixel will be needed, called color depth. Next is the number of distinct color that can be represented by pixel depend on the number of bits per pixel. So as we know, digital information is stored as bits and each bit has two values in binary language, 0 or 1. Therefore, more the number of bits per pixel, more will be information stored. So as each bit has two value, two or two or more bits per pixel can give rise to combination as multiplex of 2, that is 2 raised to power n, where n is number of bits per pixel. So 4-bit image will have 2 to the power 4, that is 16 colors. 8-bit image will have 2 to the power 8, that is 256 color, and so on. Now, next important question is why we need computational image analysis. Probably with a couple of examples, we will understand. Try to look into middle of this picture and you will find it's moving, but it's actually static. Next example is, in this slide, you will look at the color of inner boxes. It might look that some boxes are orange and some are red, but they are not all or same color. Also, an image in the right has both the block of same color. Next example is, in this picture, if you look the size of or in this picture, if you look the size of organza circle in both the right one look smaller, but it is not. Both are equal. Similarly, both the line on right images are of same size. Next example is, even further, if you look into this image, can you figure out where this image begin and where this image ends? Probably no. So all these pictures are basically indicating optical illusion, and they indicate that our eyes are perfect for analysis and can be biased by context. So we need computational analysis. So although although there are many tools for image analysis, we in this training are using open source and most widely used tools called ImageJ. So it was previously called Fiji. It was developed by National Institute of Health, USA, almost 37 years ago. It is Java-based program, and the advantage is that it can run on any platform like Windows, iOS, Linux, or Android. Beside microscopy analysis image, beside microscopy analysis, ImageJ is used for a lot of other type of analysis. So now let's start our practical session. So you'll have day 2 folder where we'll have sample plot and images software. So let's begin. So now let's switch to the practical session. So this practical session of mine is divided into two practicals. In the first practical, we will learn overall known how to image J, particularly understanding of important menu, opening the documents, installing plugin for microscopy related work. And second practical will be about merging two images of different tagged fluorophores. So I hope you have already installed ImageJ and updated your Java and instructed in the email provided during the training program. So let's now begin our practical one. The first step in this practical is to understand various menu formats required for microscopic image analysis. As I have already, okay, so I now request you to open the image by clicking on the shortcut image, shortcut of image J icon as I am doing it. So let's see first how to open a microscopy image in image J. So there are two ways of doing this. First, it is by using menu command like file, open, and you can search the location of file. And second is by dragging and drop. So now you can go to your Google Drive Day 2 folder where you are provided with some sample image for analysis. So it is suggested that you download all those images on your desktop as I have done here. So now click on file, open, and choose the location on day 2 folder. So I have saved in desktop, day 2 folder, and open the file name confocal 3 fluorophores. I am opening it, as you can follow me. Okay. So this way, this was one way of opening the file. The second one is direct drag and drop into image menu, like dragging and drop. Okay. So now let's have a look at some important menu and commands which will be useful in analysis or analyzing microscopy images. So you can see a number of small icons just below file menu like rectangular, oval, polygonal, freehand, etc. Selection, like selection and many others. So these are the tools for selecting a specific area which is often known as region of interest or ROI in image analysis terminology. When you select a specific area and then you use different command from the command menu, so I'm choosing this oval shape icon and okay. So likewise you can choose other option like rectangular or polygonal or freehand selection. So and next is we can use different commands from the command menu in image like image adjustment, brightness and contrast, or color change or copy paste. All those things will be applied to the selection region. So the second important command is changing the image type. For this, go to image menu, choose type. We'll see a number of options like 8-bit, 16-bit and 32-bit, etc. At this point of time, our image in RGB format. RGB means red, green and blue. As these three basic color constitutes all color on computer screen, so this is optimal format for colored image acquired from various sources. So I want to change the image type. So for changing image type, you can simply click on any of option I suggested. So let's convert this into 8-bit image, which will make this image on grayscale. Beside this file format conversion, we have two other important menu to be used. That is adjust command, by using which we can modulate contrast images, contrast and brightness and color balance of the image. So let's first go to image again, then choose adjust. By using this command, I am showing you how to change brightness and contrast of the images. So just a minute. We'll change brightness and contrast in RGB images. So go to image, adjust, brightness and contrast. Will increase the contrast and minimize the brightness. So uh, so I showed you how to change brightness and contrast of the image, but we should remember that this has to be done under ethical guidelines for microscopy image manipulation. All right. Similar to this brightness adjustment, if you want to control or change specific color tone, then we have to use option like again go to image, choose adjust, okay, and click on color balance. This option you will see red. If you want to change the contrast or brightness of red color, you can minimize or maximize. Likewise, if you want to change green color, you can again maximize or minimize. And likewise, uh, blue color. So, but I would say that this has to be done under ethical premises. So, into yet another command that will be useful in our analysis called split channel. As you can see in this picture that there are three different colors. One is blue, which is the color of nucleus, as it is stained by blue fluorophore named DAPI, and Violin mitochondria have been stained with red color using microtracker red, and my green color is microtubules of cytoskeleton have been stained with phalloidine conjugated to elixir which is showing, like as I have told, green color. Now if you split three components, we can use a command split channel, and for this you have to go to again image, color, and split channel. So by doing this, so you would observe that the image has been escalated into three different channel or three different file, in which you can see the name of channel. See the name here, you can see the name of channel on the top of file name. So you can observe here that nucleus, you can observe here that nucleus which was stained with blue dyes is predominantly visible in blue channel. All right. Mitochondria are visible in red channel and cytoskeleton is visible in green channel. But you can also see presence of nuclei in green channel and fin cytoskeleton in red channel, which indicates that nucleus contains some green fluorescence and cytoskeleton has some red fluorescence, which was not visible to our eyes. So this discrimination is possible by using split image option, as we have seen this, and we will use it during a microscopy image analysis. Now, finally, let us learn about how to install plugin. So plugins image required for various different type of analysis, and they can be directly downloaded from different website sources provided by the people who have developed them. In this case, I will give you example of installing a cell counter plugin. For this, I have created a cell counter shortcut. So for this, you can click on the link which is provided in your day2 folder and then download the jar file. Clicking on this cell counter.jar file, I have already downloaded. So now simply you what next is, I have downloaded, let me show. Okay, so yeah, so uh, you have to copy this jar file by Control C and open local disk C, your C file and C drive, and open program files where I have downloaded image J. Open image J and again open plugins and paste your jar file, cell counter jar file here. So I'm copying it. What you have to do, go to cell counter dot jar file, download it, go to your C drive and open program files where you have downloaded image J, open image J, then open plugin file and paste there that cell counter.jar file. I hope you got that. So um, now, now I can close my image J. So I have closed my image J and I am reopening it. When I will do so, I'll be able to see the plugin name in my image J plugin menu. So I am checking it whether it is, yeah, see. So file is appearing in plugin file. So I hope this was clear to everyone. If you have any question, you can ask. After that, we'll start our second part. Let us now start our practical 2. Uh, you in this practical will be merging two images obtained from epifluorescence microscopy. So as you have learned in theory that different type of fluorophores can be used to tag different molecules in the cell in order to visualize co-localization or distribution. So the first part will be looking at co-localization of nanoparticles with the reactive oxygen species in the cell. So before starting the practical, we should understand one important thing, that images from epifluorescence microscope can be obtained in two different ways or formats. First one is channel splitted images in 8-bit, where each type of fluorescence will be recorded in the different type of image and they appear in grayscale. And the second type is RGB images, red, green, blue images, which will look colored. So first, let us start with opening image again, opening image. So we will start our practical with split channel images. So we are going to use the same command, like first file open, or by simple dragging and drop. I'm dragging and drop the files. So this time you have to open two files. First file name green channel ROS here. So I'm uploading it by simple dragging and drop. Okay, and second one is red channel nanoparticles. Okay, so sorry, just a minute. Yeah, so now, okay, once we have opened these two images, we will use a simple command to merge these two channel. So go to image menu, click on colors, and then choose merge channel. Okay, so when we do so, software promote us to choose representative images of channels, and we assign these two images to specific channels. So I'm assigning it like, uh, nanoparticles is red channel, and green channel is ROS. Click OK. So what did you see? By doing so, when you click OK, we get a final images that contains both channel in one, and we can see that red tag nanoparticles are co-localized with reactive oxygen species at only some places, while most of them are outside, as this was an early time point images. So we have to keep one thing in your mind, that computer and this program cannot see colors, and whatever we assigned, whatever we assign to, it will generate the image of some type of colors. It will assign wrong channels, then it will provide false coloring of fluorophore, as we can see here. Let's again open this two images. I'm closing it. Again open these two images, and we'll again merge it. So I'm opening again. Okay, so it was just a minute. Green channel and red channel. All right, and again merge them, like image. So go to image, color, and merge channel. And this time we will assign nanoparticle as blue. So blue images, and um, ROS as yellow images. So here ROS as, click OK. So what did you see? You'll see that the must images has wrong colors or false color, which do not represent actual fluorophore. All right. Now I hope you got this. So now let's move into the next part of practical. Okay, so this time let us perform the same process by using another set of images, which are not split channel but RGB, that is red, green, blue images, and appeared colored. So for this experiment, we'll be looking at co-localization of uh, nanoparticles in the skin cell. Here, nanoparticles were tagged with the red fluorophore, while nucleus was tagged with blue stain DAPI, as we have told in earlier. So let us import two images in your open day 2 folder. Here's uh, two images. As you can see, that is first in nuclei. I'm dragging and drop. Just a minute. Yeah. Yeah. And second is Syria NP. Okay. Now, if you want to merge these two images, we can simply use this command like we have done for many times. Uh, Image, color, merge channel. Okay, but directly doing this step may lead to errors. So as I have told you in my as I told earlier, so that as I have told in my presentation, that our eyes are not perfect. Therefore, it is necessary that red color that you are seeing does not have any other color, and blue images that you are seeing does not have any other color. Like red have red color, blue have blue color. So let's analyze this by splitting the channel of individual images and retaining the desired channel. So this can be done by simple command, as we have done earlier. go to image, color, go to image color, and then click split channel. Okay, so what did you see? Now you will see that first image has been splitted into three separate channel. Fortunately, just a minute. Okay, so the green channel and blue channel are okay. Yeah, just a minute. So I'm doing it again. Uh, I am dragging and drop the Syria NP, and second one is nuclei. So it sometimes create problem by dragging and drop. Like, okay, so what I was saying is uh, so let's analysis this by splitting the channel by of individual image and retaining the desired channel. So that can be done by simple command, as I have said, image, color, split channel. So go to image, color, split channel. All right. So, okay. Now you will see that first image has been splitted into three separate channels. So fortunately, the green channel and blue channel, here you can see the green channel and blue channel are blank for the first image, which means that there is no blue or green color in the first picture. So now we repeat the same process for second images. So we are fortunately enough that in green color and blue color there is no images. So I'm doing it again for nuclei, image, color, split channel. So here, so and what we observed that although the second image was looking blue, this is second image. So second image was although looking blue, but it has some green and red color. So now you should have realized that what we see by our eyes may be misleading, as this image had some green color and some red color which we don't need. So now what we have to do, we will simply destroy the file of other channel which we don't need. So I'm okay. So okay, I have destroyed that file we don't need, and I'll just keep red channel for my nanoparticles file and blue channel for my nucleus file. Now, before merging these two images, we can also do additional adjustment for the background. As we can see slight color tint in the background, this can be simply improved by using the option image, adjust, and brightness and contrast. So we have to do in that way. So only background become dark and the intensity of cell is not affected. So I am doing it for and I'm increasing the contrast and the brightness. Okay, or doing it for same for Syria nanoparticles. Again increasing the contrast, like you can see the changes. So little increasing the contrast and minimizing the brightness. Not so more. Okay, apply. So so what next is, now finally we are ready to merge these two images. So for this, go to image, color, merge channel, and you'll see a beautiful merge. Okay, before that, again we'll assign reddish Syrian nanoparticles and blue is nuclei. Okay, now did you see? So this merged images, which is clearly showing the co-localization of nanoparticle in the cell. So now you can see, so now you can save this image uh, by going to file menu and choosing save option, as where you have to keep this file. So there is many different format in this uh, uh, like many formats which the image can be saved. So most commonly we use JPG format or TIFF format, but if you want small size files, PNG is also a good option. So I am doing this in PNG format, and you can follow me accordingly. So okay, this same images has been published in a paper by Dr. Aditya Arya, which you may refer in free times. Like I'm opening this. So this paper has been published by Dr. Arya. All right, so now finally we will also look at merging of the fluorescence images with phase contrast. So in order to do so, we will open again uh, 3 images. Like earlier we have opened 2 images, now we are going to open 3 images. 2 of the images are the same. nanoseria and nuclei that we have used previously, the red nanoseria file and blue, okay, it's already open, and blue nuclear file. But there is another file named phase contrast here. So first I'm going to open Syria again by dragging and drop. And second, nuclei, again by dragging and drop, or you can open by file, open, upload. And here third one is phase contrast. All right, okay. So let's not repeat the same process. We split the channel for red and blue images and delete unwanted filters. So then we adjust the brightness of these two images. So I'm doing it. We can also do some brightness adjustment in phase contrast images. Okay, so I'm quickly doing it and then merging all of three images. So for Syria, splitting channel, so I'm deleting like I have done before. I'm deleting unwanted image. Again, I'm doing for nuclei, and again deleting unwanted image like blue, red, blue is skipping, I'm keeping, and green and red is deleting. And for uh, phase contrast, I'm again splitting, and here I'll keep green. And will assign name by clicking image, color, then adjust, and brightness, will adjust brightness one by one. Minimize the brightness, maximize little contrast, maximize the little contrast. You can do it by yourself. As far we have learned so much. Go to images, adjust brightness, adjusting brightness, eyes, apply. Okay, for face contrast. Okay, clicking, adjust brightness, contrast, and maximize, apply. Now what we'll do is merge channel. So Syria will give red color, and blue as nuclei, and here will give gray to phase contrast. Okay, so now we have merged these images. Like now you can see merged file of these images. So if you have any doubt or question, you can ask me.